So this is a session that I do before HBase Con where we talk a little bit about what HBase is so that you've come here expecting to learn HBase. Well, we also need to actually go through and learn about HBase before you can understand some of the basic concepts behind it. So incredibly important that you go through this, understand this, and we're going to try and pack in as much as we can into 40 minutes so that you can understand what the rest of the sessions are saying. So when they say a region server, when they say a region, we need to understand all of this. So this is what we are. This is what HBase is at its core. If you go back and you're tasked with trying to explain to the rest of your team, this is what we're going to do, this is what HBase is, these are the very basic things that you can tell them. That it's a NoSQL data store and that's built on top of HDFS. So as we store data, all of that data is going to be stored in HDFS. As a result of that, we're going to have some interesting things like reliability, durability that we can use because everything in HDFS is stored 3 times. And HBase makes particular use of this so that it can handle failures in a different way than we're normally used to. We also have a column family oriented database. So column family oriented means that instead of being in the spectrum or the family of NoSQL databases, this one is column family oriented. We'll actually see what that looks like at a future slide, but that's a basic description. It's also based on the Google Big Table paper. We're going to see some Google Big Table people here today. We also have our HDFS once again. And here's what's important for us as data engineers as we work at scale. It's not very much good just to store data. What we have to do is we have to be able to gain some sort of value from our data. It's incredibly important. If we have a terabyte in HBase and we can't get at that data, we can't analyze that data, it's of no good to us. So we have to be able to either retrieve it quickly with a very specific get, or we need to be able to process it in large aggregates with either MapReduce or Spark or some kind of processing engine like that. That's where we get our value, by doing a large aggregate batch of getting information. So here are some very basic use cases for HBase. One of the key important things that you should take away today if you're brand new to HBase, HBase is not all things to all people. Incredibly, incredibly important that HBase is not a silver bullet. There are very specific use cases that HBase excels at. Some of these are when you need big data. If you're coming in here thinking that big data is in the gigabytes, unfortunately you're wrong. Big data is in the terabytes to petabytes, where you may not have that data now, but you may be scaling to that level. At some point in the future, you're going to hit a petabyte, for example. You also need high throughput, where if we're going to have millions of transactions, millions of inputs per second, that's one of the use cases for HBase. Another use case is to actually have a use case for NoSQL, where we need some columns to be variable. In other words, some columns will appear, some columns won't appear. And we'll see an example of that in a second. Here's another important one, and that's called random reads and writes. If you come into and you say, my use case for HBase is to randomly read something out from this petabyte, that is a good use case. Or I need to randomly write something so that it's right near the rest of them physically, that's another good use case. But if your use case and you're coming in and saying, I have a petabyte and I usually read all the way through that petabyte and analyze it all at once, generally not a good use case for HBase. So we really want to understand what randomness is so that we use HBase for the right things. And we'll talk a little bit more about this later on. So to understand HBase, we're going to need to understand a little bit about our architecture here. So here are all the daemons for HBase, and they're color-coded. So here in the green, we have our HDFS services. As you remember, HBase uses HDFS as its storage mechanism. So that's all in green. So we have our name node, we have our passive name node, our standby name node. We also have our data nodes. And if you'll look, what is it co-located with? So on the top, those are master servers. And then on the bottom, those are slave daemons. So these are the ones tasked with running the region server. And this is where the actual data storage happens for HBase. What you'll notice if you look very closely at this, that our data nodes are what are called co-located with our region servers. This is an important thing because by co-locating together, we're going to be able to get better performance together, where the region server is going to write locally to that machine, and then that will then go around to other machines, if you understand how HDFS works. So once again, our region server is the thing for HBase that does the work. It's the one that's responsible for storing the data, for getting the data, for running our scans. It's responsible for several things. But then we have another process that runs as a master, more of a coordination. And this is our HBase master. And you can see that there in the top in the yellow. This HBase master is responsible for doing all the coordination, doing some of the things that knowledge needs to be spread throughout. And as you can see by the ellipsis, there are more than one masters. What we need to have is we need to have high availability as much as possible. So when one of those masters dies, one of the other masters will pick it up. In order to do this coordination, we use a zookeeper quorum. And as you can see there in the gray box, that zookeeper quorum is there, and there are multiple machines, usually between 3 and 5. That'll be one of the more contentious things that you'll hear today is how big should your zookeeper quorum be? And by doing that and how big your zookeeper quorum is, that's how you're going to figure out things that are coordinated. Data that needs to be shared amongst all the nodes. Things like which region server is serving up which region, that sort of information. And you also see that we have our yarn server there in the blue. Our yarn service is going to do the processing. That's the incredibly important part. If we just store this stuff, that's one thing that's interesting. To be able to process and aggregate, now that's where things really become interesting. So what is NoSQL? So let's take a look at what NoSQL, our table architecture, looks like. You remember me talking about what a NoSQL table is, what HBase is? It's a column family-oriented database. Well, here's what a very basic one looks like. There on the top, we have column descriptors. These, if you're coming from a relational database background, you might think of this as a column name. It says, here's the name of this piece of data that we're going to store. Then we actually have our table. You might think of that more as a namespace, where here's all the data that we're grouping together. We have our row keys there on the left. This is what uniquely identifies a row so that we can access this data. And as we'll see in a second with some code, this is how we access that data. This is how we pull that data together and actually go through and access it. Then we have our data itself. So here we have Todd Lipcon, for example. Okay, that's NoSQL at its very basic. Looks very much like a relational database. So let's see how it looks different from a relational database. Here, the key thing is that column family-oriented database that we were talking about. Instead of all the data just being stored in one place, these column families manifest as both a logical and a physical manifestation of difference. So all the data is stored together, all of the data for a column family is stored together, physically stored together. So here's all the data for one column family, here's all the data for another column family. As a result of doing that, we can do some interesting things, and we can group commonly used data together so that it can be read faster as a result. So that's generally what we do with column families. We can group data together to read faster. We can group data together because it has similar characteristics. So we can do settings on a per column family basis. We could say, here we look at this column family. Here's some text. Here's a bunch of JPEGs. Do you think that those will have different characteristics as a result? Do you think that they'll have, which one do you think will compress better? Should we even use compression on JPEGs? Probably not. Should we use compression on the text data? Probably yes, because there are some benefits. As a result of storing different pieces of data in different column families, we're able to make the best use of our resources as a result. One important thing is that the column families are, the row key identifies the data all the way across the row. So whether it's in one column family or another, that's how we'll uniquely identify them. Then we get into more of the NoSQL. And this is where we get to see some of where NoSQL is very, very different from a relational database. Here we have a few rows. Here we have columns without some data. For example, Andrew doesn't even have an image. Well, should do, for example, if we were to do this with a relational database, we would have to store a null there. There has to be the non-existence of something. We have to say, relational database, there's nothing there. It is nullable. Well, with HBase, instead of actually storing a null, what we do is we just wouldn't store anything at all. The non-existence of something would be the null. As a result of not having to store nulls, we can be more efficient as a result. Another interesting thing is that we can have multiple versions. And depending on your use case, this may be very interesting to you. It may be very nice to be able to go back in time and say, well, it looks like this now. What did it look like last time and the time before that? When we store these new versions, we can actually look back at the timestamp for them and say, what did it look like at this time? What did it look like at that time? By doing these sorts of operations, we can do some interesting things with our data. Sometimes we're having to do this manually. So now what we have is we have these previous versions, but we also have one thing, and this trips people up. This is where you get into a philosophy I like to call, can you do it, should you do it? So as you can see there in the L name, there's nothing that says that everything has to be a string. We could have strings mixed with integers, for example, 1,337. Okay, we can do that. It's not an error. HBase is not going to go through and say, hey, wait. You put a string there, you've got an integer everywhere else. That's not an error. This is something that HBase says, give me bytes. And we're going to see that later on. We just give HBase bytes, and we work with that data. Now, can you do it? Yes. Should you do it? I don't think so. But you may have a use case where you want to do that. So how do we start breaking this data up? How do we start working with data? How do we get it to our unit of scalability is what I think of it as. So you remember how we talked about HBase scaling to petabytes? How do we go about actually manifesting and serving up a petabyte? Well, in order to do that, we're going to have to work with our data, and we're going to have to split it up. A single computer cannot serve up a petabyte. What we can do is have many different computers all serving up a smaller portion of this to, in aggregate, actually store a petabyte. And this is how we do that. We do that with regions. And our regions are basically I like to think of it as our unit of scalability. We're going to take that petabyte, we're going to break it up into very discrete sections, and then we'll have lots of different machines serve that up. You remember in the previous slide we showed here are a bunch of region servers? Well, each one of those region servers is serving up many of these regions. And this is another thing that you'll probably hear today is how many regions should a region server actually serve up? But we're going to focus on what the regions are. So you remember how I mentioned that they're discrete? Well, regions are from one row key to another row key. And that's how we break up that region. Now, how do we go back about writing something? This is important to understand because we're actually going to have to understand at a basic level a pretty decent amount to work with HBase properly. So to give you a little bit of background, I wrote the HBase class, and what is important about that class is it wasn't just a programming class, it wasn't just an operations class, it wasn't just an architecture class. You're going to have to understand all three of those pretty well. It's more like a DevOps class in order for you to be successful with HBase. You're actually going to have to understand how a write works. So here we have a write. So in a very basic sense, a client says, ask a question to the HBase master, and which region server is serving up this particular key that I'm interested in. So you remember we had those row keys? Well, you're going to say, I'm interested in this particular row key. The very first thing that has to happen is it has to figure out which region is serving up that row key 1, and then 2, which region server is serving up that row key. Then what will happen, and this is important to understand, that the client will talk to that region server directly. We don't want to have a single place or a single thing where everything flows through. This is a bad thing for distributed systems. It adds a single point of failure, it adds bottlenecks. So as much as possible, we're going to talk directly to the piece of the daemon that's serving up that data. And in this case, it's a region server. We're going to talk to that, and we're going to write that data directly there. Now let's talk about the inverse. Let's say we're going to read some data. Well, take a wild guess. What we're going to start with is, I'm interested in this row key. We need to figure out where that row key lives and where that row key is being served up. Then, directly, and this is also important, it's going to read that data directly from that region server that's responsible for it. So, very, very important, as we see how this data moves around, that it's all being done for us behind the scenes, but we need to understand this to make the most efficient use of our resources possible. So, the API. So HBase has a Java API. This is primarily what we're going to work with because it's the only first-class citizen as of right now. However, there are some other programmatic ways that we can do this. We have a REST interface. If you are interested in that REST interface, you can go to my website at jesse-anderson.com and read some more information about it. There's also a Thrift interface. This is my personal predilection, is to use the Thrift interface if you can't use Java. Reason being is you'll have a better binary interface for working with data. Then there are some other interfaces that we'll talk about and you'll learn about over the course of of today. And these are what are called non-native non-native SQL interfaces. What that means is SQL is not built directly into HBase. Please help me convince Stack to build it in, because I think it should be there. But as of right now, we don't have a SQL interface that's built in to HBase. You're going to have to layer that on using somebody else's project. So there are various projects that'll be represented here. Phoenix. The Phoenix team has layered on that. We also have Presto. We also have Impala, Hive. There are various ways for us to write SQL queries, but have them executed by other things, other processes, so that we can get that data back. I'm sorry? Grid? Grid? Oh, drill. I don't know. Is there a MapR person here that can answer? I don't know. So here we have our puts. This is an important part for us to understand how data is being stored by HBase. Here is the very basic code in order for us to take data, store it in HBase, and that's called a put. And what we have here, we're creating our table connection, but this put is what we're interested in. Everything in HBase is bytes. Bytes, 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 bytes. And we're going to be using this bytes class, this is a helper class, quite often, because it's going to take some kind of string, it's going to take some kind of integer, take it back into our byte, into a byte array, so that we can start working with it. In this case, our row key needs to be a byte array. As a result of doing this, using a byte array, we can do various interesting things. But I do generally recommend that you have your row key in as a string. There's some reasons behind that, especially for SQL. Then we take that, we create that put, and then we do an add column. So here we have our column family as a byte array, our column qualifier as a byte array, and then we actually have to take our, in this case we're doing a double, and we're taking that and changing it into a byte array as well. So guess what? When you put things into HBase, you're actually going to have to know how to pull it back out. So there's nothing in HBase that says you put a decimal there. You're going to actually have to figure that out and keep track of that. So you remember why, when I was talking about should you do it, or can you do it, should you do it? In my opinion, the reason you shouldn't do it is because you'll have to figure out what it was on the other side. From there, we do our table.put. So when we do that, we've put data in. Now let's pull that data back out. So here we do our get, and just like before, we need our bytes. We need a byte array of that data. We need to pull that and create that get. Using that get, we do a table.get. That gives us back our result object. From there, we do a get value. Our column family is a byte array. Our column qualifier is a byte array. And that's going to give us back a byte array. Here I am really highlighting. It's just a byte array. It's up to us, it's up to our code to figure out what is that byte array supposed to be. What actually was there? What did we put there? Well, We have to know that because we're going to have to say bytes to double, or bytes to string, or bytes to integer. We're going to have to take that 32-bit integer. We're going to have to take that double. We're going to have to take that float. We're going to have to remanifest that back to the primitive that we were expecting. Does everybody understand? So very important, because you're going to have to deal with this. So as much as you're seeing me talk about straight byte arrays, there are other better ways to store data in HBase. For example, Abro. That's another way, but outside the scope of our introduction here. So that's the quick and dirty of API. Now let's talk about the quick and dirty of architecting our solutions. So I can't stress this enough. If you take away just a few things out of this material or out of today, if you use HBase like you would a relational database, it will cause you many, many problems. So when you think about, and if you were to imagine yourself sitting in a room and you're having a meeting and you're doing a design meeting about a relational database solution, the first things that you're drawing up on the whiteboard are relationships. How does the customer table relate to the order table? How does the invoice table relate to the customer table? You're thinking about relationships, okay? When you talk about and you think about and you architect things for HBase, it's about how are you accessing the data. It's a very, very different meeting. It's a very, very different conversation that you're having. And this is one of the biggest shifts that you're going to have to make as you start to work with HBase. When you sit in those meetings and you're talking about what you're going to do, you're going to be asking, how is this data accessed? What sort of data? What pieces of the data are you accessing together? What are you doing? How are you doing that? Rather than, how do I relate this to this? Your focus is going to be on that because you're going to be saying, how is this data going to be accessed? You need to understand how it's going to be accessed because you're going to be putting them together in column families together. You're going to be thinking about how you create an Avro schema. But you're also going to be thinking about what is the fastest way I can read and write that data. You're going to be favoring denormalization instead of normalization. So if you're coming from a database background, you're favoring normalization. You're favoring a highly normalized specification of data, where ideally a piece of data is only stored once. Let's say zip code for a customer. Well, the stark difference for HBase is that zip code may not be stored once. It may be stored 100 times. And you're making a very specific choice to store it 100 times because you want that data to be stored as fast as possible. You're taking a bet that you're going to read far more often than you're going to write. So you're going to change that zip code or postal code maybe once every 1,000 times. But the other 999 times, you're going to read that data. And you're going to take that bet because it's going to be far better customer experience. You're thinking about how do I access this data, how do I organize that data, rather than what is the relationships of everything. Can't stress this enough. If you treat HBase like a relational database, it will lead to abject failure. And when I say an abject failure, I really do mean an abject failure. I've trained at other companies, and these companies have embarked, one company was 4 months in, 5 months into a very, very big project. We're talking about millions of dollars spent, a team of 20 people. And what they did is they said, okay, we're moving from a relational database into HBase. They said, okay, we have table A in relational database. We'll create table A in HBase. Table B in relational database, table B. They did a one-to-one thing. And they did not go through the questions that I asked in the previous slide. They did not go through and say, how is this different? How am I accessing data? How am I doing this? They just said, okay, let's take this relational database and we'll do the exact same thing. This is the recipe for an abject failure. It's very, very important that as you come away from this session, you're thinking about HBase as a very, very different animal. So what did that failure manifest as? It manifested as primarily the app was incredibly slow. In fact, the app that they were creating was slower than the relational database by far. It wasn't like there was a speed up. they had increased their complexity of their apps significantly because they were having to do vast amounts of joins. It also manifested as significant product slippage. It manifested as a lot of different problems. So I really want you to take away from this and say, we're not going to use it like a relational database. We're going to be treating it very different, as a very different animal, so that we use it the right way, use it the way that we're supposed to be. So to that end, we actually have to put some engineering into engineering that we've never done before. And so if you're coming from a relational database background, what you're going to have is, you're going to have said how much you could total the amount of time that you've spent on thinking about what a row key should be on one hand. So total lifetime before HBase, I had spent maybe 1 minute thinking about what that ID should be. It's either going to be an auto-incrementing number or it's going to be a GUID. One of those two. Well, it's a very different thing for HBase. We're actually going to think about this because we have one go at our index or our key. That means that when we go to access that data, do you remember when we were doing the get and we had just that one key to do the get with? Well, that means that we have one go at creating the right key for us, creating that right primary key. So what we don't do is we don't just create an auto-incrementing number. We may use a GUID, but we're actually going to put some effort into all this. We're going to actually think about what is the right key. And one of the things that we might do is actually have multiple pieces of data within that key. That's called a composite key. We might have multiple pieces. Instead of just a GUID for a customer, we might have a GUID for the customer as well as some other information about what was happening during that key. And that is going to give us some extra power behind the scenes to do scans, do more advanced gets as a result. So then row key design is just one portion. Then we have our schema design. So we have to put more effort and more thought and more design into our table schemas. In my opinion, probably the biggest and most difficult part isn't so much the design, it's talking to the people to get how they're going to access the data so that it's designed properly. Does that make sense, everyone? So good. So your meetings, instead of your PMs, your project managers, or the various people who are the sources of knowledge, may be used to relational database meetings where you're talking about relationships. And now when you start to talk about how am I accessing this and how am I grouping this data together, their minds may explode like those jet commercials. So it'll be a little bit of difficulty for your part where you're going to have to train them and you're going to have to say, so we're going to be doing it this way all along. Now we're going to have to talk about it this way. And we're going to have to talk about how we access this data. So this access pattern has to be known ahead of time. In some cases, it has to be guessed or divined. In some cases, it's going to have to be you cajoling it out of some person, some business person. So it may be something difficult for you that you'll have to do. So what we have is some very general best practices. Generally, what you want is fewer, bigger, more denormalized tables. So let's say at that company that I trained at, they had 50 tables. We took that down to 3 or 4 tables. Instead of you doing a join on those tables, what they did is they took all those tables, brought all of that data together so that when we read it, it was all together at once. What we'll want to do is also spend more time upfront designing. It's going to be more difficult than we'd like to change our schemas. So you'll want to get it right as best you can. That said, you're going to hear some of the people speaking today probably saying about how they had a version 1 of their schema and then they moved to a different version of their schema. That it's just an inevitable thing of engineering that we'll have to get some brand new information, that we'll have to change the way we're doing things, and they'll give those stories probably. Another thing, we want to use bulk loading if we have incremental or time series data as much as possible. So if we get, let's say there's an electrical company, or let's say you're a stock company, and you get this big file filled with trades, and instead of doing a put per line in there, what you'll do is you'll do what's called bulk loading. You'll process that entire file, and then you load it into HBase. and it's far more efficient that way. So those are some general best practices there. So with that, I'll open it up to some questions. But a little bit about me, I'm Jesse Anderson from Smoking Hand. You can email me here at jesse@smokinghand. You can follow me on Twitter. I'm at Jesse T. Anderson.